Happy Thursday. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 3 different classes that may be participating in this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. So, today we're going to finish up section 11.5 eventually, but first of all, we've got some questions. So let's get started. This is from 11.5 part 1, and this is number 5. And I want to change the screens here. And this particular question, can you see the WebAssign screen now? Somebody tell me, yes?
Yes.
Yes.
Thank you. All right. This problem, I think I'm actually gonna delete it after this quarter because students get confused by it. And frankly, I found it confusing because the way it's lined up is not the way I would do the problem. Let me explain. Okay, so you've got the formula A equals PE to the RT, okay? And you're told that P is 1,000, R is 6% or 0.06, and T is 10. Okay, so the first question says A equals blank e to the 0.06 times something power. And what they're doing is they're having you fill in the blanks. So if you look at this first line here, so P is 1,000 and R is given, and then T is 10. Okay, so then that leads you to this line, because if you take 0.06 times 10, you get 0.6. Okay, so now we've got 1,000 times e to the 0.6 power. Now, from there, you could just punch that all into your calculator. But what they're doing is they're saying, okay, e to the 0.6 power is this big number here. Okay. So the 1,000 is what they wanted in this box down here. All righty, so that you'd write 1,000 times, and then this red number in parentheses comes from e to the 0.6 power. That's what's going on there. I know it's confusing. It's sort of a case of, like I say, I would have just taken this whole line here and done it all at once. But if you did just this piece here, you would get this. So then you'd still have to take it times 1,000. Okay, and that's all I've got to say about that one. Then we're going to go on to number 14. And let's take a look at that. It says, using the formula A equals P times e to the RT power, given the following values of P, R, and T, round to the nearest hundredth. Okay, so P is, hang on, P is 18,000. R is 10.7%, which would be 0.107, and T is 60 years. Okay, so filling in the numbers, we would have A equals 18,000 times e to the 0.107 times 60. Okay, so putting that all into my calculator, I'm going to put in 18,000. Then I'm going to go second function e to the x, which is going to give me this. Then I'm going to put in 0.107 times 60, close up the parentheses, and hit the equals button. Okay, so having said that, let me actually do it now. Let's put on some glasses here, and I'm going to go second e to the 0.107 times 60. And when I do that, I get 1105205.05. It says to round to the nearest hundredth. So I end up with 11,052,056.05. All right, are you okay with that? Let's see, next up on the list is 16. And let's take a look at that. Kind of forgot which screen I was showing you. So 16, basically the same idea. A equals P e to the RT. P is 563. R is negative 0.6%, which would be negative 0.006. Is that right? 1, 2 places, yeah. And then T equals 9 years. So plugging the numbers in, A equals 563 e to the, let's see here, negative 0.006 times 9. So on my calculator, 563 second e to the x, negative 0.006 times 9, close it up, equals 563 e to the x, negative 0.006 times 9. And I get 533.404276. So that's 533.40, rounding to 2 decimal places because the 4 would round down. All righty, that takes care of those questions. Anything about those before I move on to the next set? Okay, let's see here. 4765 and there 11.5, number 19. Okay. It says evaluate the expression without using a calculator. And what we have is the natural log of 1 over e. Okay. Now, natural log is the same thing as log base e. So we have the log base e of 1 over e. Okay. Now, I don't know what that's equal to yet, so I'm going to say, well, it's going to be equal to some unknown quantity that I'm going to call box. If I take this logarithmic equation and put it in exponential form, it would look like this. E to the box equals 1 over e. If I could get this expression or this equation so that the bases were the same on both sides, then the exponents would be the same. Well, on the left, the base is e. On the right, the base is not e. I could take 1 over e and write it as e to the negative 1 power, moving it upstairs. So now the box is negative 1. And there's the answer to that one. Any questions there? All right, we're going to go on to number 20. Evaluate the expression without using a calculator, the natural log of the 6th root of e. So again, this is log base e of the 6th root of e. Whoops, that's supposed to be an e in there. Like that. I'm going to set that equal to some unknown box. Now, changing this into an exponential equation, e to the box equals the 6th root of e. But the 6th root of e would be e to the 1/6 power. So the box equals 1/6. So there's your answer. Okay. And finally, number 21. We good to go on? Okay, no objections. I'll keep going. The natural log of the 9th root of e to the 4th power. So this is log base e of the 9th root of e to the 4th power, which is equal to some unknown. Changing it into exponential form, e to the box equals the 9th root of e to the 4th. But this, the 9th root of e to the 4th would be e to the 4/9 power, exponent on top, index on the bottom. So the box is 4/9. Okay. Takes us to another group. Let's see here. We have 4770. And there. 11.5.1. Number 5. Okay. So here, this problem number 5 is just like the one I did earlier, where what they were looking for was 1,000. Okay, so it's really the same idea as before. So I'm going to go on and let's take a look at 14. Okay, so 14, find a using the formula. A equals PE to the RT. So A equals 16,000 times E. I don't know if this is the same numbers as before or not. I know it's the same interest rate, but raised to the 0.107 times 60 power. So your equation is going to look like this. Okay, so I'm going to take 16,000 second e to the x, and then so I've got 16,000, then inside I'm going to put that times 60 equals, so 0.107 times 60, and I get 9824049.826. The 6 is going to round up, so 9824049.83, comma there, comma there. So that would be your final answer. Okay. Questions there? All right. Number 15, same idea. Whoops. A equals P times E to the RT. And it says the principal, or the P, is 15,896. E to the negative 7%, so negative 0.07 times 14. The reason I use this for times is because on my calculator, that's how it shows up, but that's times. Okay, so here again, 15,896 second e to the x, negative 0.07 times 14, and I'm getting 5965.945, and the 100th place, the 5 and the 1,000th place would round up, so you'd end up with that. Okay, and that takes care of that person's answers. And let's see here. So I want to make sure I'm on the white screen. So now let's see, we've got this one, 11.5. Starting with number 11. Okay, so we're going to look at a graph here. Graph the function e to the x plus 2. All right, Consider this. The graph of e to the x is approximately 2.7 to the x power. What do we know about that? Well, this is what we should know. We know the domain's all real numbers. The range is greater than 0. And there's a y-intercept at 1. Okay? That's y equals e to the x. Well, of these 4 graphs, this first one looks like it would be approximately y equals e to the x. But what does the +2 do in the exponent part? It moves it to the left 2 units. So which of these graphs is like 1 but moved to the left 2 units? Well, let's go through and eliminate it. Obviously, the final answer can't be 1. It can't be 4 because it's been shifted down. So it's either got to be this one or that one. If we take this graph and we move it 2 units to the left, let's see. This point right here looks to be about 1. Keep in mind this scale is different, so it's about 1, 2. If we take 1, 2 and move it to the left, it would be at -1, 2. Let's see. -1, 2, yeah. No, it's got to be this one. Are you following my logic there? Any questions there? Okay. So that would be this graph here. Okay, number 12. Think back again to parabolas. If you had something like y equals x squared, and then you put a coefficient in front of it that was bigger than 1, it stretched it, made it thinner and taller, where if it was between 0 and 1, it kind of made it wider. So what is the 3 going to do? Well, here again, this bottom one, yeah. Actually, let's do this. Let's think about where would your y-intercept be? That might be enough information right there. If x is 0, what's y? What's 3 times e to the 0 power? Well, what's e to the 0 power? What's anything to the 0 power other than 0 to the 0 power?
1.
1. What's 3 times 1?
3.
So when x is 0, y should be 3. Ta-da, it's got to be this one down here. See what I'm getting at there? You don't necessarily need to find the entire graph. Of these 4, that's the only one that has a y-intercept at 3. Okay, that was 12, 13. Okay, 13, 14, 15, and 16. I'm going to skip those because I already did several just like that. The person that asked about these, you know who you are. If you still have questions about them, when we're done here, email me and I'll get in touch with you and go over them. But for the sake of time, I don't want to redo those. Again, they're all going to be the same thing we did. Notice here on 15, you've got to put in -0.04 kinds of things. Okay. And that actually takes us back to some problems from 2 days ago. Let's see here. I'm not sure what thing I'm showing. Let's go back to the white screen. And I'm going to go through these kind of quickly because it's from a previous day. Come on, let's see. Okay. This goes back to the idea of changing back and forth. So this is back in 11.4, but I just want to take a look at number 24. It says solve for x. Log base 27 of 3 equals x. So if you change this to an exponential equation, you get 27 to the x power equals 3. On the right side of the equation, I basically have 3 to the 1 power. There's an implied 1. 27 could be written as 3 cubed. So 27 to the x becomes 3 cubed to the x. but a power raised to a power, you would multiply the exponents. So now you get 3 to the 3x equals 3 to the 1. Therefore, 3x equals 1 and x equals 1/3. Okay. Let's see. 29. Number 29. It says evaluate the logarithmic expression.
Mr. Nail, we can't see the white screen.
Oh, sorry. And you couldn't see it before either? My bad.
No.
Okay, let me go back here. So back to this one. Can you see that now?
Yes.
Sorry about that. Sometimes I forget to push the right button. So number 24, we had log base 27 of 3 equals x. So I changed it into an exponential equation. 27 to the x power equals 3. 3 is the same thing as 3 to the 1 power. 27 is the same thing as 3 cubed. So instead of 27 to the x power, I've got 3 cubed to the x power. But a power raised to a power, you multiply the exponents. So now I get 3 raised to the 3x power equals 3 to the 1 power. Since the bases are equal, the exponents are equal. From that, we get 3x equals 1, divide by 3, x equals 1/3. Sorry about that. Okay, we good? All right, number 29, evaluate the logarithmic expression. Log base 2 of 512. Okay, log base 2 of 512. Well, I don't know what that's equal to, so let's call it box. So changing it to an exponential equation, 2 to the box equals 512. Well, 512 is 2 times 256, which is 2 times 2 times 128, which is 2 times 2 times 2 times 64, 2 times 2 times 2 times 8 times 8, 2 times 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 2, 2 to the 9th power. So 2 to the box equals 2 to the 9th power. So the box equals 9. Okay. 33 and 34 are similar. I'm going to go on for the sake of time. The person that asked about those, if you still have questions, please email me and I will be happy to go over them with you. But we do need to move on. All righty. So now, let's get rid of that. And everybody can see my white screen, correct?
Yes.
Okay, so now we're going to look at 11.5 part 2, the sequel. So we've had this formula, A equals P times 1 plus R over K to the KT power. And we've had this formula, A equals P times E to the RT power. This is for compound interest. That's monthly, quarterly, daily, weekly, annually, whatever. This is when something is growing or decaying continuously. So this question says, the introduction says, continuous compound interest. So that means we're going to be using this formula, okay? Continuous compound interest. An initial investment of $2,000, so that's P is going to be $2,000, earns 8% interest, so R is 8% or 0.08, compounded continuously, so that's why we're using this formula. What will the investment be worth in 15 years? So our equation becomes A equals $2,000 times E raised to the 0.08 times 15 power. So really, this is just like a problem we did earlier today. In fact, a bunch of them. Okay, and then e to the 0.08 times 15. And it says, let's see, It doesn't say anything about rounding, but since we're dealing with money, we would round it to the nearest cent. Now, this thing goes on out here, rounding to the nearest cent, the 3 would round down, so we would get $6,640.23. Any questions on that one? All right, let's take a look at another problem. This says determining previous balance. So we're going to go backwards. We know the final amount. We know A. We want to determine the initial amount, P. So we're still going to use this formula. It says an account now contains $3,610 and has been accumulating interest at 8% annual interest. Compounded continuously. Now, actually, before I read that, we wouldn't have known that we were going to use this formula, but I knew ahead of time because it says compounded continuously. How much was in the account 4 years ago? So the time is 4 years and P is our unknown. Okay. So now filling in the numbers, I get 3,610 equals P times e to the 0.08 times 4 power. All right. Because I'm going to solve for something on the right that's mixed up and all that other stuff, I'm going to go ahead and simplify this further. And I'm going to take 0.08 times 4, which becomes 0.32. Okay. Now, to solve for P, I'm going to divide both sides by e to the 0.32 power. So P equals $3,610 divided by e to the 0.32 power. Okay. So 3610 divided by, second calc, e to the 0.32 power, close that up, and I get 2621.398. We're talking money, so we're going to round to the nearest cent. The 8 will round up, so we're going to get $2,621.40. Okay, because we're going backwards. We know we had this much at the end. We had the 3610 at the end. This is how much we started with to the nearest cent. Okay with that? All right. New problem. Bed bugs. Yeah, here's a nice problem. This will make you sleep well tonight. It says, if not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. Now, growing exponentially. So we're not going to use the compound interest formula that's for days, weeks, months, whatever. We're going to use A equals P e to the RT, okay? Because we're talking continuous exponential growth. All right. It says, if a colony currently has 50 bed bugs, how many will there be in 6 weeks? So P is 50. R is 65%, which would be 0.65. Time is measured in weeks because, again, let me read it. It says, if not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. So time is in weeks. How many will there be in 6 weeks? So time is 6 weeks. All right. So A equals 50 times e to the 0.65 times 6. So on my calculator, 50 second e to the x, 0.65 times 6, close it up, and I get 2470.122455. We're dealing with bed bugs, so we'll round off to the nearest whole bed bug, which would be 2,470 bed bugs. All right with that? Okay, new problem. This says the big easy. I'm not sure what that's all about, but maybe you know. Anyway, it says New Orleans has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase in population remains constant, how long will it take for the population to double? Now, because we're talking about a population, it's going to be growing or decreasing continuously. So we're going to use A equals PE to the RT power. Okay, what do we know? It says if the current 8.2% annual increase in population remains constant, so that means that R is 8.2%, which is 0.082. How long will it take for its population to double? So the time is the question mark, but they didn't really tell us the population, and they didn't really tell us the final amount. What they did tell us is that they want that beginning population to double. All right? So let's say the beginning population is just P. If we double P, what do we get?
Two P.
2P. So the final amount, A, whoops, I wrote it wrong. A equals 2P. Now, you might be going, well, we still don't know what it is. We aren't going to need to know, as you will see. So since A equals 2P, my equation becomes 2P equals PE to the 0.082 times T. Okay, so I replaced A with double P or 2P. Now, I can divide both sides of this equation by P, and I get that. See, we divided P out, so we don't even need to know what it is. Now, if it's 0, we couldn't divide by 0, but if there was 0, there wouldn't be any population. We wouldn't be talking about this problem at all, right? Okay. So now I have an equation where my unknown is part of the exponent. So what am I going to do to solve this? I'm going to take this exponential equation and I'm going to rewrite it as a logarithmic equation. So this becomes log base E of 2 equals 0.082 T. All right, let me stop right there for a moment. So that's my playing an inning of baseball, so to speak. Base is the same and the players change. But this could be written natural log of 2 equals 0.082 T. Okay? Now, how would you solve this for T? You would divide both sides by 0.082. Okay? So T equals the natural log of 2 over 0.082. Are you okay with that? I guess so. So we'll go to our calculator. The natural log of 2 divided by 0.082 and I get 8.4530, etc. And here, let's see, they round to the nearest 10th, so it'd be about 8.5 years. Okay. Now, careful, make sure, I'm going to go on to the next screen for a minute. This, let's see. When you put it into your calculator, you push the LN button. It gives you parentheses. You put in a 2, then you need to close that parentheses and then go divided by that. Because if you don't, it might think, depending on your calculator, that you want the natural log of this, which is not what you want. Okay, so you need to close that top part up before you divide. All right, so I want to go back here. Notice, again, it didn't matter how much the starting population was, okay? But we knew that the ending population was twice as much as the starting population. So no matter what P that starting population is, we ultimately would have ended up with that after the P's canceled out or reduced out on both sides. And from there, we would have gotten this and et cetera, et cetera. But take a look at this. This is the natural log of 2. What is this number in the denominator? Where did that come from? That was R. So that gives us a formula, and this is what the formula says. The natural log of 2 over R. If you want to know how long it takes to double a population, you can just take this formula and plug R into it, the natural log of 2 over R, and get the answer. So let's do that now. What did we know? We knew that the R value was 8.2%, which is 0.082. So how long is it going to take? It's going to take that long, bada boom, bada bing. And basically that takes us right to there without all of this extra calculating. Okay. In fact, this formula right here is in the textbook. It's on page 956 in the hard copy. As far as the e-text, I don't know what page, but it's section 11.5. Okay, so you've got that formula for the doubling time. So let me ask you this. If this is the formula for how long it takes for something to double, what would the formula be for how long it takes something to triple?
Would it be log 3 over 0.082?
The natural log of 3 over
Oh.
whatever R is. Not just log, but natural log, right?
Okay.
Okay. In fact, let's go back. Let's do this problem now. This problem says doubling money. How long will it take $1,000 to double if it is invested at an annual rate of 5% compounded continuously? All right. So the principal is $1,000. We want it to double. So we want it to end there. And the annual rate is 5%. And the question is how long? So could we use that shortcut formula on this? Absolutely. The time would be the natural log of 2 divided by 0.05. Natural log of 2 divided by 0.05. It's going to be 13.86. So we'll say 13.9 years about. Okay. So that works when you're going to double a population or an amount or something. And if it's growing continuously, you can use this formula. You can always do it the long way, which is what I did here, but you end up with the same result and it takes you less time. All right, any questions on that? Back here, let's do this one. It says triple money. Find the length of time for $25,000 to triple when it is invested at 6% annual interest. So the time would be the natural log of 3 over 0.06. Natural log of 3 divided by 0.06, and it's approximately 18.3 years. That's all I need to do. I don't need to take it through the A equals PE to the RT. I can do all of that, and I'd be happy to if you want me to, but if you're doubling or tripling something, again, tripling natural log of 3, doubling natural log of 2. Okay? Any questions on that? All right. Let me see if there's anything else I want to do here. I think we're good. Tell you what I'm going to do. I am going to go, well, no, I guess I did those. Yeah. I'm going to call that quits for today. And as I said, if I didn't get to your questions, email me. I'd be happy to talk you through them. But the stuff that we did was pretty much like the questions that other people asked that I didn't do. I'm going to stop the recording.